Mars is a mirror for our dreams and nightmares. To the naked eye, the planet exhibits a reddish hue, blood red in the imagination, god of war, star of judgment. Through a small telescope, it is the most Earth-like of planets, with cinnabar deserts and white polar ice caps. A world we could imagine visiting, perhaps even settling in. 19th-century astronomers convinced themselves they saw plains and mountain ranges, and canals delivering meltwater from high latitudes to arid equatorial cities. Some thought the Martians a peaceful civilization, far in advance of our own. Others saw threat. Across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes, wrote H.G. Wells in his classic science fiction novel The War of the Worlds in 1897. The nature of Mars remained a mystery until well into the 20th century, because the planet is small and far away, and therefore difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images which would not at first sight have prevented Wells from publishing. With a little imagination, the ice caps, high clouds, and dark regions circling the deserts could be mistaken for evidence of a water cycle feeding the seasonal advance and retreat of vegetation. Photographs from the first flyby of Mars by NASA's Mariner 4 spacecraft on the 15th of July 1965 abruptly laid to rest the romantic notion of Mars as Earth's habitable twin or potential foe. These images revealed an arid surface reminiscent not of our blue planet, but of our desiccated moon. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. And contemporary accounts of the impact of the Mariner 4 flyby suggest that this was a powerful realization. In November 1965, the Bulletin of the Atomic Scientists carried an article entitled "The Message from Mariner 4," and the message was bleak. The shock of Mariner's photographic and radiometric reports is caused not only by their denial of the terrestrial image of Mars, but by the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson was reported as commenting, it may just be that life as we know it, with its humanity, is more unique than many have thought." The hesitation in the first few words is revealing. Here is Mars as a symbol of our cosmic isolation. It is as though deep, or perhaps not so deep, in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that the Earth is far more fragile and precious than a dispassionate analysis of their Cold War brinkmanship might suggest. Or perhaps the perspective delivered by exploration is always shocking. Apollo 8's Earthrise, the photograph that delivered such a positive end to a troubled 1968 by setting the blue Earth against the grey moon, was 3 years away. But Red Mars provided a foretaste. In response, Carl Sagan co-authored a paper suggesting, somewhat playfully, that all was not lost. Mariner 4 took only 22 photographs with a resolution of over a kilometre, in a strip crossing the region in which the astronomer Percival Lowell had sketched canals from his observatory in Flagstaff, Arizona at the turn of the 20th century. From the warmth of the Arizona desert, Lowell wrote that Mars was chilly, but no more so than the south of England, which certainly supported a civilization of sorts. Using several thousand photographs of a similar resolution taken by meteorological satellites in Earth's orbit, Sagan and his co-authors found only a single feature that unambiguously indicated the presence of a civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization had it flown by Earth. We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it. The non-existence of an extant Martian civilization was confirmed by the Mariner 9 mission in November 1971, the first spacecraft to orbit another planet. Mariner 9 achieved a photographic resolution of 100 meters per pixel, and no sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the combined results of the suite of microbiology experiments carried by the spacecraft are not considered to be unequivocal, because Martian soil chemistry is, to coin a phrase from the official NASA report, enigmatic and could conceivably have masked any biological activity. In hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles further from the Sun than Earth, and receives less than half the solar energy. It is a small world with a tenuous atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in the Gale crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning it has experienced minus 120. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than of intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides, and rivers wound their way through valleys, carved by a water cycle from land to sky and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock because it is a small planet far from its star. But the geological evidence is unequivocal. The surface tells a different story. Mars, then, remains an enigma. As a wandering red star, it stirred the imagination of the ancients. As a telescopic image, too small and shifting for visual or intellectual clarity, it became our twin. When spacecraft flew by, it shocked us into considering our cosmic isolation. The red planet was relegated in our collective consciousness to the status of just one more rock, glistening in the night. Then we landed, and discovered a world that was once habitable, and could be again. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity and volcanism have erased the deep geological past, Mars has been relatively quiescent for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient cataclysms documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s and provided detailed maps with colors corresponding to differences in altitude. Just as on Earth, there is significant variation, but the geological features on our smaller sister world are much bigger and bolder. The highest elevations on Mars are found on the Tharsis Rise, a great volcanic plateau and home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Everest, Olympus Mons towers 25 kilometers above the lowlands of Amazonis Planitia to the west, and its base would fit inside France just about. Cutting a deep scar across Tharsis to the southeast of Olympus Mons is Valles Marineris, named after the Mariner 9 spacecraft that discovered it, a canyon that dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. The atmospheric pressure at the floor is twice that at the rim, high enough for liquid water to exist on the surface in a narrow range of temperatures. These are extreme altitude differences for a small world, over 30 kilometers from the summit of Olympus Mons to the floor of Hellas. On much larger Earth, for comparison, there is only 20 kilometers difference between the summit of Everest and the Challenger Deep in the depths of the Mariana Trench. The most striking and ancient elevation difference on Mars is that between the northern and southern hemispheres of the planet, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometers lower in altitude than the southern. There is no consensus as to how the dichotomy formed, other than that it was early in the planet's history, and before the large impacts which created the Utopia and Chryse basins around 4 billion years ago. At some later time, the northern lowlands were resurfaced by volcanic activity in a similar fashion to the smooth lunar seas, which accounts for their lack of cratering relative to the much more ancient terrain to the south. The oldest terrain on Mars is found in the Noakis Terra region of the southern highlands. It is characterized by heavy cratering reminiscent of the far side of the Moon. Even small craters in the Noakian highlands are heavily eroded, which suggests the regular, if not persistent, presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls, forming interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world, at least occasionally. The evidence is written across the land of Noah. In contrast, the younger terrain of Hesperia Planum displays much less evidence of regular erosion by water, but bears the scars of occasional catastrophic floods that cut deep valleys over very short periods of time, and may have formed temporary large lakes or seas. The Amazonis Planitia region shows little sign of flowing water, fewer impact craters, and less evidence of active volcanism, suggesting it was formed more recently, when Mars was significantly less geologically active. The persistence of surface features over many billions of years in the Noakian, Hesperian, and Amazonian regions has led to the historical epochs of Mars being named after the distinctive terrains that still bear the characteristic marks of the climate and geological activity that formed and sculpted them. The Noakian period was the earliest and wettest, and coincided with the origin of life on Earth around 4 billion years ago, when conditions on both worlds appear to have been very similar. The Martian atmosphere may have been denser than Earth's and dominated by carbon dioxide, but significant questions remain about how such an atmosphere could have warmed Mars sufficiently to deliver the warm, wet climate, and how that atmosphere was lost. The MAVEN spacecraft, currently in orbit around Mars, aims to answer this question, as we'll discuss later in this chapter. The Noakian period ended as Mars became increasingly cold and arid around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period, the time of catastrophic floods, ran from the end of the Noakian to around 3 billion years ago, when Mars entered its current frozen, arid phase, punctuated by occasional volcanic activity and the large-scale movement of ice, but with very little evidence of flowing water. The long 3 billion-year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The whys pose a significant challenge to planetary scientists. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day aridity? What happened to the water on Mars? Was it lost to space, or does it persist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still accessible? Could we exploit the ancient reservoirs of Mars to support a human colony? And perhaps most significantly of all, did life arise on the planet during the Noakian period, coincident with the origin of life on Earth? And could that life still be present on Mars today? The current fleet of spacecraft in orbit around Mars and roving across its surface has been designed to answer these questions. Mars today is a planet buzzing with activity. Communications to Earth and the Martian Internet are managed by the Mars Reconnaissance Orbiter, MRO, an orbiting bridge between worlds. MRO carries the HiRISE instrument, a camera with resolution high enough to see basketball-sized features on the Martian surface. The Mars Color Imager Marquee camera monitors Martian weather, and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, identifies mineral deposits, particularly those formed in the presence of surface water. Orbiting with the MRO is the Mars Atmosphere and Volatile Evolution Mission, MAVEN. This cameraless spacecraft operates between 150 kilometers and 6,000 kilometers above the Martian surface, measuring the composition of the atmosphere at different altitudes and observing how the tenuous gases are stripped from the planet by the solar wind. Mars Odyssey is the veteran of the orbiting fleet, having arrived in 2001 and still being operational in a polar orbit, searching primarily for water ice on the surface. Mars Express is a European Space Agency mission that is delivering high-resolution photographs, mineralogy data, radar investigation of the near subsurface, and atmospheric measurements, including the search for methane, a gas that on Earth is associated with biological activity. India's Mangalyaan space probe is primarily a technology demonstrator, but it carries a secondary scientific package capable of investigating atmospheric composition. The newest arrival at Mars is the joint European Space Agency Russian ExoMars Trace Gas Orbiter, which will observe seasonal changes in the Martian atmosphere and search for subsurface water deposits. The spacecraft will form the communications bridge for ESA's ExoMars rover, due to land in 2021. The two most recent explorers of Mars are the Opportunity and Curiosity rovers. The Opportunity rover landed on the Meridiani planum close to the Martian equator on the 25th of January 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to the Jet Propulsion Laboratory's engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018, after over 14 years and a journey of 45 kilometers on the surface of Mars, exploring the Endurance, Victoria, and Endeavour craters. On the 13th of February 2019, Opportunity was finally declared dead. Opportunity's younger and far larger companion on Mars is Curiosity, the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. The enormity of the mission is best described through the words of Alan Chen, operations lead at NASA for the Curiosity mission, at 10:31 PDT on the 5th of August 2012, watching the landing at the Jet Propulsion Laboratory alongside the team. The engineers described it as 7 minutes of terror. 7 minutes to maneuver a spacecraft that had taken 8 years to design and build, with a program cost of more than $2.5 billion, from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface of the planet. The tension reflected the high stakes. The Mars Science Laboratory mission, to give the lander and orbiter their full title, was a high-risk flagship science mission in the same category as Voyager, the Hubble Space Telescope, Viking and Cassini, and was beset by cost and schedule overruns and controversy. This is in many ways unsurprising. New technologies and ambitious scientific objectives are difficult to implement and achieve, and in part because of this deliver great rewards. In hindsight, nobody would question the value of any of these missions, which have delivered some of the greatest insights and most inspiring images in the history of exploration. Yet this never prevents bean counters and rival scientists with agendas, and more charitably, budgetary challenges of their own, whinging and even considering cancellation. This is naive. Funding for science is almost always grudging from a political class whose view of the acquisition of knowledge is utilitarian. The far deeper value of exploration as a critical part of the internal voyage of our species, bringing us into direct confrontation with the mystery of our existence, is lost on them, at least until occasional Johnsonian president, not Alexander Boris de Pfeffel, moments. It may just be that life as we know it with its humanity is more unique than many have thought, and we must remember this. Which means that a cancellation of one project does not mean an uplift in funds for another. More likely the budget will be lost to science. At the time of writing, the same issues plague another NASA flagship mission, the James Webb Space Telescope. As Robert D. Baum wrote in an op-ed article for Space News in December 2008, at the height of the Mars Science Laboratory controversy, when implementing flagship missions, cost and schedule overruns are not uncommon, but history shows that the mission return often eclipses the expenditure. The Hubble Space Telescope experienced a development cost overrun several times its approved project budget, and was launched much later than originally planned. In hindsight, would any rational space scientist not concede that the return from Hubble was worth the investment? Given the febrile atmosphere, however, no amount of philosophy or reason would mitigate the costs of failure of the Mars Science Laboratory mission. A landing accident was both possible and unthinkable. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not trivial, which is perhaps why the chosen engineering solution seemed, not to put too fine a point on it, daring. Mars has a thin atmosphere, so slowing down a spacecraft when it's travelling around 10 times faster than a bullet is hard. And yet the atmosphere is thick enough to apply sufficient frictional heating to destroy a spacecraft without adequate protection, and turbulent enough to cause significant uncertainty in the landing site of an unsteered vehicle. This renders the more obvious engineering solutions redundant. You can't simply deploy a parachute and float to the surface. The 1970s Viking landers used a combination of heat shields during aerobraking, parachutes, and retro-rockets with success. But the Curiosity engineering team dismissed this tried-and-tested solution. It did not allow for high enough precision, or for the gentle landing required for the pinpoint delivery of a large rover with delicate wheels. The Viking landers had legs built like tanks. The Viking landers also carried their heavy descent rocket systems with them to the ground, which didn't matter because they stayed put. Curiosity would have had to lug all this unnecessary mass around Mars for years. The Opportunity rover, her sister ships Spirit and the earlier Mars Pathfinder, employed a combination of aerobraking, parachutes, rockets, and airbags to cushion the falling spacecraft. But these previous rovers were lightweight in comparison, at just over a fifth of the mass of the gargantuan Curiosity. A rover of this size and complexity bouncing over the surface in an airbag cocoon was not considered feasible, primarily because of the sheer mass of the airbag system needed to cushion the impact. The lightweight Opportunity rover's landing system was almost twice the mass of the rover itself. The chosen Entry, Descent and Landing Procedure, EDL, for Curiosity, was described by mission lead Adam Stelzner as the result of reasoned engineering thought. A beautiful example of the truism that reasoned engineering thought and common sense, at least of the sort possessed by the average golf club bore, do not always match up. The Curiosity EDL appears to the untrained eye to be bonkers, or maybe overcomplicated, but it wasn't, and it worked. Tucked up inside a protective shell, Curiosity encountered the outer layers of the Martian atmosphere, 125 kilometers above the surface and traveling at around 20,000 kilometers per hour, at 10:23 p.m. Pacific Daylight Time on the 5th of August 2012. The spacecraft, at this stage cocooned inside a protective enclosure, flew entirely under the control of its onboard computers, with no input from mission control on Earth. This was the first time an autonomous guided entry system was employed for an interplanetary mission. using a combination of thrusters and the ejection of balance masses to shift the center of mass and trajectory of the spaceship and guide it with a design accuracy of around 10 kilometers towards the chosen landing site. This guided rather than ballistic trajectory allowed for a much wider choice of landing sites for Curiosity than for the previous landers, which required around 100 kilometers of flat, safe land surrounding the nominal touchdown point. But it also required the rover to fly itself. The round-trip travel time for a radio signal to Mars was over 13 minutes when Curiosity landed, making control from the Jet Propulsion Laboratory in California impossible. During the first stage of descent, a heat shield constructed from a unique material known as pica, phenolic-impregnated carbon ablator, protected Curiosity from peak temperatures of around 2,000 degrees Celsius, generated by friction in the thickening Martian atmosphere. 4 minutes after beginning the entry phase, slowed to just under 3,000 kilometers per hour, Curiosity's parachute deployed at an altitude of 11 kilometers above the surface. The supersonic parachute is a vast and complex structure, 80 suspension lines over 50 meters long, attached to a 16-meter canopy. Having slowed to a velocity of 700 kilometers per hour with the help of the parachute, the heat shield was jettisoned at an altitude of 8 kilometers, allowing the onboard radar to get a view of the ground and deliver high-precision altitude and velocity measurements. With the parachute fully unfolded in relatively dense, low-level Martian atmosphere, Curiosity drifted in the Martian sky for 80 seconds, descending ever more slowly. At an altitude of 1.8 kilometers, traveling at a sedate 280 kilometers per hour, the NASA timeline calls for a deep breath as Curiosity separated from the parachute system and dropped in freefall towards Mars. For engineers, says the NASA website, it's like jumping out of a plane for the first time. The freefall drop was designed to allow Curiosity to separate far enough from the parachute system so that it wouldn't accelerate back into it when 300 meters further down, its retro-rockets fired and the powered descent phase of the landing began. For the Viking landers, this was the final phase. But for Curiosity, after the rockets had delivered the rover to an altitude of just 20 meters with a descent velocity of less than 1 meter per second, almost a hover, the audacious final phase of the landing protocol kicked into action: the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an umbilical cord of electrical connections 7.5 meters in length. 4 of the rockets, angled away from the vertical so as not to damage the rover, continued to fire, allowing the whole delicate system to approach the surface at walking pace. At 5 meters from the surface, Curiosity unfurled its wheels, stowed for the 8-month journey from Earth. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface and issued one last command through the electrical umbilical up to the sky crane: "I'm down, cut the cables, and fly away." After a 500 million kilometer journey, Curiosity was delivered safely to Mars, just 2.4 kilometers from its nominal landing point. A triumph of engineering ingenuity and brilliance. Curiosity was sent to Mars to explore Gale Crater, a 150-kilometer wide impact crater formed during the late Noachian or early Hesperian period, when liquid water would have been present at least occasionally on the surface. In the great tradition of astronomy, the crater is named after the Australian amateur astronomer, planetary observer, comet hunter, and occasional banker, Walter Frederick Gale, who discovered a host of comets as well as a number of geological features on Mars at the turn of the 20th century, using self-built telescopes in his backyard. The primary reason for choosing Gale Crater was the unusual central structure Mount Sharp, or Aeolis Mons, which rises over 5 kilometers above the crater floor. There is still debate about precisely how Mount Sharp formed, but the layers visible from orbit along its flanks suggest that it is the weathered remains of sedimentary rocks which once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor once more, while leaving the towering central structure intact. Deep, exposed sedimentary layers are extremely enticing to geologists, because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forwards through Martian time, and scientists are close behind. Joy Crisp, the deputy project scientist from NASA's Jet Propulsion Laboratory, explained the choice of landing site in the weeks before launch. Mount Sharp may be one of the thickest exposed sections of layered sedimentary rocks in the solar system. The rock record preserved in those layers holds stories that are billions of years old, stories about whether, when, and for how long Mars might have been habitable. Just as the layers of exposed rock in the Grand Canyon on Earth reveal the story of our planet, the exposed sedimentary layers of Mount Sharp are a storybook that the winds of Mars have opened, ready for Curiosity to read. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp, stopping along the way at each interesting site to characterise the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysis of the Martian surface and the layers just beneath. NASA loves acronyms. Curiosity acquires samples using the SSS, the Surface Sampling and Science System. It is made up of 3 parts: the SASPAR, Sample Acquisition, Processing and Handling Subsystem, SAM, Sample Analysis at Mars Instrument, and CHEMIN, Chemistry and Mineralogy Instrument. The main components of SASPAR, which is mounted at the end of Curiosity's robot arm, are an integrated scoop and sample processing system, Chimera, and a drill for acquiring surface and subsurface samples. The Scoop and Sample Processing System surely has one of the most inventive of all NASA acronyms. CHIMRA, pronounced Chimera, after the multi-headed creature of Greek mythology, which stands for the Collection and Handling for In Situ Martian Rock Analysis Tool. Someone deserves an award for that. These are transferred into SAM, which includes a gas chromatograph, a mass spectrometer, and a tunable laser spectrometer, and CHEMIN, the first X-ray diffraction experiment ever flown in space, and the most sophisticated modern technique for characterizing mineral samples on Earth. The science returned from Curiosity is only just beginning, as older data are analyzed and published, and new data from its climb up the slopes of Mount Sharp and through Martian geological time continues. But current results are consistent with, and greatly enhance the detail of, our picture of a planet that was warmer and wetter when Gale formed around 3.5 billion years ago. In early October 2012, Curiosity rolled to a halt at a place the geologists christened Rock Nest, and scooped up a handful of Mars. The sample of dust, dirt, and finely grained soil was fed into the SAM and heated to 835 degrees Celsius. The baking process revealed the presence of significant amounts of carbon dioxide, oxygen, and sulfur compounds. SAM's analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rock Nest didn't just provide circumstantial evidence for ancient water. Around 3% of the sample's mass was water, suspended as small ephemeral droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A transient landscape of ancient streams, deltas, and ponds is bounded by the border of the crater. When alighting on ancient riverbeds running down from the crater's rim, Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all the necessary building blocks for life. Summarizing the results in August 2017, Michael Mayer, NASA's lead scientist for the Mars exploration program, said, "A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes." In June 2018, 2 new discoveries strongly reinforced the idea that Mars was once a habitable world, and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface, in rocks known as mudstone that form from silt deposited on lake beds. This means that all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more tantalizingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today, reaffirming and enhancing previous observations of methane spikes from orbit. The important additional information from Curiosity was that the methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not irrefutable evidence of life on Mars today by any means. It's thought that geological processes may be able to account for such a seasonal variation, although if this were Earth, a biological explanation would be favored. The appropriately cautious Michael Mayer had this to say in June 2018. "Are there signs of life on Mars? We don't know. But these results tell us we are on the right track." Science is a humble and cautious pursuit, and from the time of Viking we've known that Martian soil chemistry is notoriously complex and can easily catch out the unwary scientist. So we should leave it there. Curiosity continues its journey through Martian geological history emboldened. It is certainly driving across an ancient lake bed where, for a reasonably extended period over 3 billion years ago, conditions were favorable and all the ingredients for life were present. While we shouldn't speculate or read too much into the results to date, we can let our imaginations wander for a moment to picture what Gale Crater might have been like during the late Noachian, when life was gaining a foothold on her sister world. We stand on the shores of a lake partially filling Gale, fed by runoff from snowmelt on the far northern rim. Where Mount Sharp now stands, a small island breaks the surface blue, not the mountain of today, but a small central peak left over from the impact. A place of grand beauty, where each Martian evening the pale sun sets in the west beyond the island, rays glinting dimly off the still waters, interrupted by the shadow of the peak out to the crater's edge. A sundial, marking the passing of time, on a lake populated by microbial Martians.
The Earth is replete with features named after rogues, because history is the province of the rich and powerful, and the deserving rarely become either. To find more worthy geographical nomenclature, it is necessary to look further afield, to a place that escaped the attention of the vain. The dark side of the Moon is such a place, because nobody had seen it until the Soviet spacecraft Luna 3 photographed it in 1959. It isn't dark, by the way. It permanently faces away from Earth due to an effect called tidal locking, and receives the same amount of sunlight as the familiar Earth-facing side. The first humans to see it were the crew of Apollo 8, when Bill Anders memorably described it as looking like a sand pile my kids have played in for some time. It's all beat up, no definition, just a lot of bumps and holes. Lacking the smooth lunar maria, the dark side is an expanse of craters, and many of these have been named entirely appropriately after deserving scientists. Giordano Bruno is there, of course, alongside Pasteur, Hertz, Millikan, D'Alembert, Planck, Pauli, van der Waals, Poincaré, Leibniz, van der Graaf, and Landau. Arthur Schuster, the father of the physics department at the University of Manchester, is honoured. And tucked away in the southern hemisphere next to a plain named Apollo is a 65-kilometre-wide, partly eroded crater called Leavitt. Henrietta Swan Leavitt was one of the Harvard computers, a group of women employed to work at the Harvard College Observatory by Professor Edward Charles Pickering. By the late 19th century, Harvard had collected a large amount of data in the form of photographic plates, but the professional astronomers had neither the time nor resources to process the reams of material. Pickering's answer was to hire women as skilled and cheap analysts. Scottish astronomer Wilhelmina Fleming was his first recruit, whom he employed after proclaiming that even his maid could do a better job than the overworked males at the observatory. Fleming became a respected astronomer. She was made an honorary member of the Royal Astronomical Society in London, and amongst many important published works, discovered the Horsehead Nebula in Orion. Buoyed by this successful policy, Pickering continued to expand his computers throughout the later years of the 19th century, bringing Henrietta Leavitt into the team in 1893. Pickering assigned her to the study of stars known as variables, whose brightness changes over a period of days, weeks, or months. In 1908, Leavitt published a paper based on a series of observations of variable stars in the Small Magellanic Cloud, which we now know to be a satellite galaxy of the Milky Way. It consists of a detailed list of the positions and periods of 1,777 variable stars, and towards the end a brief but extremely important observation. It is worthy of note that in Table 6 the brighter variables have the longer periods. It is also noticeable that those having the longest periods appear to be as regular in their variations as those which pass through their changes in a day or two. This discovery immediately caught the interest of Pickering, and for good reason. If a star's intrinsic brightness is known, then it is a simple matter to calculate its distance. Put very simply, the further away an object is, the dimmer it appears. Leavitt and Pickering published a more detailed study in 1912, in which they proposed a simple mathematical relationship between the period and intrinsic brightness of 25 variable stars. This relationship is known as the period-luminosity relation. All that was required to calibrate the relation was a parallax measurement of the distance to a single variable of the type observed by Leavitt. If this could be achieved, then the distance to the Small Magellanic Cloud could be obtained. In 1913, the Danish astronomer Einar Hertzsprung, in a spectacularly accurate piece of astronomical observing, managed to measure the distance by parallax to the well-known variable star Delta Cephei. Delta Cephei has a period of 5.366341 days and lies 890 light-years from Earth, according to modern measurements by the Hubble Space Telescope. Because of its historic place as the first of Leavitt's variable stars to have its distance measured, these stars are now known as Cepheid variables. Inexplicably, even though Hertzsprung managed to get the parallax measurement and the distance to Delta Cephei correct, his published paper quotes the distance to the Small Magellanic Cloud as 3,000 light-years, which is badly wrong. The modern-day measurement is 170,000 light-years. There is speculation that Hertzsprung made a simple typographical error in the paper and for some reason couldn't be bothered to correct it. In any case, the technique had been established, and 2 years later Harlow Shapley published the first of a series of papers that refined the method and led him to the first measurement of the size and shape of the Milky Way. He concluded that the galaxy is a disk of stars around 300,000 light-years in extent, with the Sun positioned around 50,000 light-years from the center. This is roughly correct. The Milky Way is around 100,000 light-years across, and the Sun is about 25,000 light-years from the center. This was an important moment in the history of astronomy, because it was the first measurement that relegated the solar system from being the center of everything. It's true that few, if any, astronomers would have claimed otherwise by the turn of the 20th century, but science is a subject that relies on measurement rather than opinion. The journey into insignificance had begun.
The solar system is in fact a system. Although we might feel isolated on a ball of rock in the dark, that is an illusion. No planet is an island. The system evolves as one. Draw a diagram of the food chain underpinning all complex life on Earth today, and at the base, is a stream of photons generated 150 million kilometers away inside the Sun. Green plants are the interface between a star and civilization. Our understanding of Mars demonstrates that a planet's relationship with the Sun is not all light and sweetness. The star can provide the energy for life, but the solar wind can also destroy life or prevent it from ever emerging through the damage it can cause to planetary atmospheres. The solar wind emerges from the Sun's atmosphere, known as the corona. The temperature at the Sun's surface is 6,000 degrees Celsius, but the temperature of the corona is over 1,000,000 degrees Celsius, heated by energy transferred from the surface by the powerful solar magnetic field, twisted and coiled by the star's rotation. At such high temperatures, atoms cannot hold together. Electrons are ripped away from atomic nuclei, and matter exists in a fourth state, not solid, liquid, or gas, but a soup of negatively charged electrons and positive ions known as a plasma. Some of these particles are moving so fast that they escape the Sun's embrace completely, streaming outwards across the solar system at velocities in excess of 800 kilometers per second. This is the solar wind. When these high-energy charged particles reach Earth, most do not smash directly into atoms at the top of our atmosphere, because we are protected by our magnetic field. They are deflected harmlessly by stretching and distorting the field out on the night side of the planet. The stretched field occasionally reconfigures, accelerating electrically charged particles back down the magnetic field lines to the Earth's poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. This is the aurora, the northern and southern lights. From Earth, the aurora can be seen by those lucky enough to be far enough north or south on the right night, when the sky is clear, the Sun is active, and the interplanetary magnetic fields are favorably aligned. From the lofty vantage point of the International Space Station, the aurora reveals itself as halos dancing around the poles. It is an unforgettable sight, undoubtedly one of nature's wonders. But as is often the case in science, and in life for that matter, the experience is greatly enhanced by knowledge. The lights, dancing faster than the eye can see or perhaps the brain can comprehend, are a direct result of the structure of atoms. Electrons shifting between allowed energy levels, determined by the number of protons in the atomic nucleus that holds them captive. High-altitude oxygen glows red. An atom is struck by a charged particle accelerated down the Earth's magnetic field lines towards the pole. The interaction shifts an electron into a long-lived excited configuration. If the atom is not involved in a collision in the thin air for around 100 seconds, an eternity in atomic time, the electron will shift down closer to the nucleus, and a red photon will be emitted. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. This time the atom must avoid collision for around a second, still an atomic eternity in the denser air. Excited nitrogen molecules add a deep red or pink to the lower edges of the towering curtains of light during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. To calculate the colors, physicists treat the electrons as waves trapped inside a deep well created by the electric charge of the protons. Particles imagined not as tiny flecks of matter, but as fields that can span great volumes of space. The energy to drive the display comes from nuclear fusion reactions inside the Sun, a factory 1,000,000 times the volume of Earth, converting hydrogen into helium at a rate of 600 million tons per second. The weak nuclear force acts slowly and grudgingly to convert protons into neutrons in the core, nuclear alchemy that results in the creation of neutrinos, which stream across 150 million kilometers at close to the speed of light before passing unhindered through the entire planet on their journey to infinity. Thus, 60 billion per square centimeter stream through your head every second without even a nudge, because your head is almost entirely empty space, and neutrinos hardly ever come close enough to interact with your sparsely distributed molecules. It might happen once in your lifetime. The nuclear forces at work inside the Sun also assembled the heavy elements that make up your body inside old stars long ago from hydrogen and helium forged in the first few seconds after the Big Bang: carbon, oxygen, nitrogen, sulfur, phosphorus, and iron. Gravity assembled the stars by forcing the collapse of primordial interstellar clouds, causing them to heat up in their centers and triggering the nuclear reactions that release the energy to halt the collapse for a few billion years, long enough for life to emerge in the gradient between the nuclear furnaces and the chill of the expanding universe. All of these thoughts are ignited in the imagination by the auroral display. Our experience is enhanced by knowledge. A central component of the web of physical processes that make the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet and allows it to return in a much subdued form to the poles. Without this, the processes that Maven observes stripping the atmosphere of Mars would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo, which is easy to explain in broad brush terms, but extremely complex and not fully understood in detail. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle, and the Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other subtleties. The rate of heat flow through the mantle is affected by geological processes including plate tectonics and volcanism. The precise nature of the flows depends on the constituents of the core other than iron, for example the sulfur content and distribution, and so on. It's fiendishly complicated, and because of this complexity, our planetary magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo, because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands, suggesting that these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. The Martian meteorite ALH 84001, dated at 4.1 billion years old, also shows clear signs of having formed in the presence of a magnetic field. These observations lead to the current baseline view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onwards, the atmosphere was exposed to the full force of the solar wind, and the Maven results tell us that this was likely the key driver for the loss of the Martian atmosphere. It would be tempting, but wrong, to suggest that the loss of the magnetic field was the trigger that drove the change from the Noachian to the Hesperian. The timescales probably don't match, and in any case the loss of the magnetic field wouldn't have led to an immediate loss of the atmosphere. Sputtering is a gradual process which still continues today. There have been speculative attempts to link the switch-off of the dynamo to the Hellas impact, or multiple impacts around the time of the late heavy bombardment. The idea is that the heating of the mantle can disrupt the heat flow out from the core, in turn disrupting the smooth convective flows. At the time of writing, the sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years in response to gravitational interactions with the other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle, and even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice tilted towards the Sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. Despite all this marvelous complexity, the simple thought with which we began this chapter probably captures the spirit of why Mars died. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more tenuously than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind, and the surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by ESA's Mars Express spacecraft. Blue ghosts of a Martian past generated by localized magnetic hotspots scattered across the planet, and the last traces of carbon dioxide in the atmosphere, energized by the relentless solar winds. Despite its 3 billion-year quiescence, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbor a solar system's lifetime away. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence for Martians within the next decade. The discovery of a second Genesis would have important philosophical, scientific, and cultural consequences. It would mean that, given the right conditions, liquid water, active geology, and a sprinkling of organics, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat and minerals and gas. We are bubbling chemistry that thinks. If it happened on 2 neighboring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not God's children, but we are also not alone. Of even greater importance, I think, is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface, and a great wealth of mineral resources, all the things that are necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. The message from Mariner 4 was not interpreted correctly. There is a second chance for us on Mars, when we feel ready to take it. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. The Earth is by far and away the best planet we know of anywhere in the universe. We were born of it, and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the new world, living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there? The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. In Werner Herzog's film Encounters at the End of the World, a man named William Gierser describes the sort of person who gravitates to Antarctica, the last of Earth's frontiers. I like to say, if you take everybody who's not tied down, they all sort of fall down to the bottom of the planet. So that's how we got here, you know? We're all at loose ends, and here we are together. I remember when I first got down here, I sort of enjoyed the sensation of recognizing people with my travel markings. I was like, hey, these are my people. PhDs washing dishes and linguists on a continent with no languages. Mars is the step beyond the Antarctic, and perhaps we all need to take it in our imaginations. Our civilization feels untethered to me. We're at a loose end, huddled in a tiny corner of our system. We watch the wandering planets and the wheeling stars and the cycles of day and night, and wonder what the hell we're doing. We're all linguists on a continent with no languages. As a consequence, we scrabble around, eking out the ever more precious resources on Earth, trying to expand and build more stuff and grow in a thin shell of air on the two-dimensional surface of a small rock, giving little thought for the three-dimensional path marked by the lights in the night. Robert Zubrin, the visionary engineer whose work has inspired, amongst others, Elon Musk, likes to say that ideas have consequences, and the worst idea in the history of humanity is that we must compete for limited resources. This is false. The solar system contains raw materials beyond our needs or desires, and they will become resources when we choose to access them. The international tensions created by the competition for earthbound resources are based on the entirely false and dangerous idea that resources are limited. False, false, false. We have the technology, and perhaps as we drift ever more aimlessly, we may discover the will to unlock the unlimited treasures in the vast solar system of which we are a part. We need to shift our collective consciousness. We burn too bright for this world alone, but that does not mean we should extinguish the flame. We must forge a new path that transcends competition between nations, that requires the wholesale rejection of the mindset that mistakenly compels us to retreat or fight over dwindling resources on a single groaning planet. We must transform ourselves into a multi-planetary, spacefaring civilization, and this begins with the colonization of Mars, an achievable goal forged from the human desire to explore and expand without pushing up against someone else's border fence or damaging our planet beyond repair. Imagine the magnificent intellectual and physical vistas, the new technologies, the opportunities, the excitement of creating a new society. The joy of extending our collective experience and hopes and dreams to a new world and worlds beyond. Mars has a pivotal role to play in our future. If we don't go there, we'll never go anywhere. And if we go nowhere, we'll die here. Breathing new life into the old red planet will breathe new life into us. It will be our first step beyond the cradle and onwards to the stars. The age of planetary surfaces. Earth before life, 4.5 billion years ago, was no nascent Eden, closer to the realm of Hades than the Garden of God. Molten and smouldering, cloaked in toxic clouds through which the young sun could barely break to signal the coming dawn. The planet still trembled from the aftermath of a glancing collision with Mars-sized Theia, now fragmented into a ring of debris that, given time, coalesced with the ejected rubble of Earth to form the Moon. 4 billion years later, two people who owed their existence to the energetic geology of Hadean Earth stepped onto the surface of the coalesced rubble and considered their position in the firmament. From their vantage point, Armstrong and Aldrin viewed a peaceful, pristine planet that has been many different worlds since its formation. How do we know? How can we speak with any authority of events that happened billions of years ago, beyond not only memory, but also life on Earth itself? How is such a timeline calibrated? The answer lies in the rocks. Apollo delivered many treasures, countless engineering breakthroughs, a generation inspired, Earthrise from Apollo 8, the simple joy of exploration. But scientifically speaking, the treasure was rock. 382 kilograms of rock collected from 6 landing sites. On the Moon, as on Earth, rocks can be dated with great accuracy, using the natural clocks provided by the radioactive decay of certain atoms. The chemical element rubidium, for example, occurs naturally and quite commonly in a form known as rubidium-87, which is found in many potassium-rich minerals. It is unstable, with a half-life of 48 billion years. This means that over a period of 48 billion years, half of the rubidium-87 atoms that were present in a rock when it formed will have decayed away, transmuting into another sort of atom, strontium-87. An older rock will have fewer rubidium-87 atoms and more strontium-87 atoms. There is a little more to it than that, of course. How do we know how many rubidium and strontium atoms were present when the rock formed? The clever part of the dating procedure is that we don't need to know. The method, called the isochron method, relies on the fact that there is another naturally occurring form of strontium, which is not produced by radioactive decay, known as strontium-86. Strontium-86 is stable and chemically identical to strontium-87. The only difference is that it has one more neutron inside its nucleus. This means that any strontium-86 atoms inside a rock today were present when the rock originally formed. By counting the number of rubidium-87, strontium-87 and strontium-86 atoms in a selection of samples taken from a rock, it is possible to calculate the absolute time elapsed since the rock formed. On Earth, some of the oldest crustal rocks are found off the southwest coast of Greenland at a place called Ishwa. Using rubidium-strontium dating, we know these rocks were formed 3.66 billion years ago, with an uncertainty of 0.06 billion years. The oldest known rock on Earth was found in Jack Hills, Western Australia. It formed 4.404 billion years ago, with an uncertainty of 0.008 billion years. All known samples from Earth's crust are younger than 4 billion years old, because the seething surface of the Hadean Earth meant that rocks were constantly being melted and reformed, resetting the radiometric clocks. The same analysis can be carried out on meteorites that have fallen to the surface of Earth from space. The majority, over 1,000 known, formed between 4.4 and 4.6 billion years ago, which is consistent with independent estimates for the age of the solar system, using, for example, helioseismology measurements of the amount of helium in the Sun's core. The youngest of the moon rocks returned by the Apollo astronauts were 3.2 billion years old, and the oldest were 4.5 billion years old. 12 of the samples were over 4.2 billion years old. The variation in age of the moon rocks at the Apollo landing site is extremely interesting and important, and it forms the basis of the most accurate technique for dating areas of the Moon from which we have no rock samples. We can make a graph showing the age of the rocks collected from each Apollo landing site, and also the Russian Luna 24 robotic sample return mission, plotted against the number of craters per square kilometre at the site. The dark blobs around the labels of the various missions will represent the uncertainty of the measurements of the ages of the rocks and the crater counts. Two very low and uncertain points from the craters Copernicus and Tycho are from rocks collected by Apollo that are thought to have been thrown into the landing sites by the impacts that created these two distinctive lunar craters in the much more recent past. Two solid lines curve up across the plot, bounding the measured points. Older sites have more craters, which is easy to understand because there's been more time for meteorite impacts to build up. Surfaces that were created in the more recent past, such as the Copernicus crater, have experienced many fewer subsequent impacts. Imagine now that there's an area of the Moon from which we have no samples, but we do have photographs of that location from space. We count the number of craters per square kilometre. Let's say we get an average of 0.0002 craters above a diameter of 4 kilometres per square kilometre. This allows us to say that the surface formed somewhere between around 3.2 and 4 billion years ago, similar in age to the Apollo 17 landing site. This is one of the simplest uses of the graph. More importantly for our purposes, we can extrapolate the graph from the Moon to Mars. We have to make some model-dependent estimates of how the number of impacts changes because Mars is a larger planet with a stronger gravitational pull, and to account for Mars's different place in the solar system closer to the asteroid belt, the source of most of the impacting objects. We can do this with some confidence, and this is the primary way we estimate the absolute age of the different regions of Mars. The Noachian terrain is the oldest and has the highest density of craters, followed by the Hesperian and the Amazonian. The northern lowlands have been resurfaced by volcanic activity in the more recent past, which we know because they're relatively devoid of craters, much like the lunar seas. In this way, the absolute dates we quote for events on Mars are all ultimately tied to the radioactive dating of moon rocks, and this is one of the main reasons why the Apollo rock samples from different landing sites are so valuable scientifically. There's another key line on the graph, a dashed line we'll call constant production rate. The number of craters plotted against age would follow this line if the Moon had been subjected to a constant rate of impacts throughout its history. The measurements follow this line until we get to the surfaces around 3.8 to 4 billion years old, when the number of craters increases dramatically, implying that in the early history of the solar system, there was a time when the rate of impacts was much greater than today. That's not surprising. We might expect that the young solar system would have been filled with leftover rubble from the formation of planets, and so a more violent place. But there is a complication. If we assume that the impact rates seen on the oldest lunar terrains, such as the Apollo 16 landing site in the Descartes Highlands, were sustained all the way back to the Moon's formation, then the impact rate would have been impossibly high. The amount of mass falling on the surface of the Moon would have been similar to the mass of the Moon itself. We know that didn't happen, so the assumption is that the rise of the impact rate curve on the graph is in fact a spike that peaked around 3.9 billion years ago, and then returned to the much lower impact rate from earlier times. This violent spike in the rate of impacts from space is known as the late heavy bombardment. The cause of the late heavy bombardment is not known, but a leading theory is that Neptune changed its orbit from inside to outside that of Uranus, and the resulting gravitational disturbance deflected a maelstrom of icy objects in the distant Kuiper belt towards the planets of the inner solar system. We might reflect on the interconnected nature of knowledge and of the solar system. Exploration of the Moon provided us with the intellectual tools to date the surface of Mars. Using the scars delivered by objects deflected into the inner solar system by events that occurred far away in space and time, beyond the orbit of either world.
On the 24th of June 1947, Ken Arnold, an amateur pilot from Scobie, Montana, was flying over Mount Rainier, one of the most dangerous volcanoes in the world. Arnold was an experienced pilot with thousands of flying hours, and this implied he was a trustworthy observer. On returning to the airfield, he claimed to have seen 9 objects flying in the mountain skies, describing them as flat like a pie pan and like a big flat disk. He estimated that the disks were flying in formation at speeds of up to 1,920 kilometers per hour. The press jumped on the story, coining the term flying saucer, and within weeks, hundreds of similar sightings were reported from all over the world. On the 4th of July, a United Airlines crew reported seeing another formation of 9 disks over the skies of Idaho, and 4 days later, the mother of all UFO stories exploded at Roswell, New Mexico, with the confirmation and then rapid retraction by the United States Air Force of a recovered flying disk. An alien craft crash-landed on Earth. I'll put my cards on the table here. I believe in UFOs. That is to say, I believe that there have been sightings of flying things in the sky that the observers were unable to identify, some of which were objects. But I do not believe for a moment that these were spacecraft flown by aliens. Occam's razor is an important tool in science. It shouldn't be oversold. Nature can be complex and bizarre. But as a rule of thumb, it is most sensible to adopt the simplest explanation for an observation until the evidence overwhelms it. My favourite response to the criticism that dismissing the possibility of alien visitations to Earth is unscientific was provided by physicist and Nobel laureate Richard Feynman in his Messenger lectures at Cornell University in 1964. Some years ago, I had a conversation with a layman about flying saucers. Because I am scientific, I know all about flying saucers. I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? No, I said, I can't prove it's impossible. It's just very unlikely. At that he said, you are very unscientific. If you can't prove it impossible, then how can you say that it's unlikely? But that is the way that is scientific. It is scientific only to say what is more likely and what less likely, and not to be proving all the time the possible and impossible. To define what I mean, I might have said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the results of the known irrational characteristics of terrestrial intelligence than of the unknown rational efforts of extraterrestrial intelligence. It is just more likely. That is all. Irrespective of the veracity of the stories of mutilated cows, crop circles, and violated Midwesterners at the hands of these alien visitors, the cultural impact of these early sightings was very real. America quickly entered into a media-fueled love affair with alien invaders in shiny discs, brandishing anal probes. Why didn't they use MRI scanners, a non-Freudian would surely ask. Of all the hundreds of thousands of references to flying saucers that began to appear in the media, a cartoon by Alan Dunn, published in the New Yorker magazine on the 20th of May 1950, found its way into the lunchtime conversation of a group of scientists at the Los Alamos National Laboratory in New Mexico. Enrico Fermi was one of the greatest 20th century physicists. Italian by birth, he conducted his most acclaimed work in the United States, having left his native country with his Jewish wife Laura in 1938 as Mussolini's grip tightened. Fermi worked on the Manhattan Project throughout World War II, first at Los Alamos and then at the University of Chicago, where he was responsible for Chicago Pile 1, the world's first nuclear reactor. In a squash court underneath a disused sports stadium in December 1942, Fermi oversaw the first man-made nuclear chain reaction, paving the way for the Hiroshima and Nagasaki bombs. After the war, Fermi settled as a professor in Chicago, but he often visited Los Alamos. During one of these visits in the summer of 1950, Fermi settled down for lunch with a group of colleagues including Edward Teller, the architect of the hydrogen bomb, and fellow Manhattan Project alumni Herbert York and Emil Konopinski. At some point, talk turned to the recent reports of UFO sightings and the New Yorker cartoon, stimulating Fermi to ask a simple question that turned a trivial conversation into a serious discussion. Where are they? Fermi's question is a powerful and challenging one that deserves an answer. It has become known as the Fermi paradox. There are hundreds of billions of star systems in the Milky Way galaxy. Our solar system is around 4.6 billion years old, but the galaxy is almost as old as the universe. If we assume life is relatively common, and on at least some of these planets intelligent civilizations arose, it follows that there should exist civilizations far in advance of our own somewhere in the galaxy. Why? Our civilization has existed for around 10,000 years, and we've had access to modern technology for a few hundred. Our species, Homo sapiens, has existed for 250,000 years or so. This is a blink of an eye in comparison to the age of the Milky Way. So if we assume we are not the only civilization in the galaxy, then at least a few others must have arisen billions of years ahead of us. But where are they? The distances are not so vast that we cannot imagine traveling between star systems in principle. It took us less than a single human lifetime to go from the Wright brothers to the moon. What might we imagine doing in the next 100 years, or 1,000 years, or 10,000 years, or 10 million years? Even with rocketry technology as currently imagined, we could colonize the entire galaxy on million-year timescales. The Fermi paradox simply boils down to the question of why nobody has done this, given so many billions of worlds and so many billions of years. It is a very good question.
The crater counting techniques developed from our exploration of the Moon allow us to place our observations of Mars today in historical context. They allow us to construct an absolute timeline. If we see evidence that water once flowed across a surface or pooled within a crater, and we can date the area using crater counting, then we can estimate when the water flowed and when it disappeared. As we've discussed, curiosity is exploring Gale and painting a vivid picture of what happened there. Crater counting allows for an estimate of when, independent from the rover's ground-based measurements. A recent analysis using images from orbit taken by MRO found 375 craters ranging in size from 88 meters to 23 kilometers inside Gale crater, implying an age of 3.61 billion years, with an uncertainty of around 60 million years. This places the formation of the crater and the geological events that played out inside it during the late Noachian, early Hesperian, and this time frame is consistent with observations of the presence of water at many other sites of a similar age. Consistency over a wide range of independent observations is extremely important in science. One site or set of observations alone may be tantalizing, but rarely compelling. Multiple independent observations reduce the uncertainty and give scientists more confidence in their understanding. When our goal is to understand the sequence of events on an ancient landscape far away that no human has ever visited, caution and consistency are both vital commodities. Since we have only one active rover at present, and landings are by their nature rare and confined to limited geographical regions, orbital observations of much wider areas of the planet are a vital tool. MRO's high-rise camera has provided some of the most beautiful and detailed high-resolution photographs in the history of space exploration, covering over 99% of the Martian surface. Features as small as a meter wide can be seen in these images, and the camera can also operate in the infrared, allowing for the identification of different minerals at the surface. There are many beautiful photographs in the MRO library that reveal evidence of persistent lakes and river systems, particularly across the Noachian terrain in the southern highlands. Sites such as the Jezero crater clearly show meandering river channels draining into deltas. Some images, constructed using both visible light and data from the spacecraft spectrometer, reveal well-defined river channels flowing out of the crater and the presence of carbonates and clays that form where there is persistent liquid water. For these reasons, the Jezero crater is one of the 3 prime targets for NASA's Mars 2020 rover. Some of the more recent finds are associated with the Arabia Terra region, which sits between the Noachian southern highlands and the great lowlands of the north, where water could have flowed towards a possible northern ocean. Researchers from University College London and the Open University studied an area of Arabia Terra equivalent to the size of Brazil, using high-resolution imagery from MRO. The study mapped a network of over 17,000 kilometers of ancient river channels, not the usual excavated dry river valleys, but rather a network of inverted channels, raised lines of sand and gravel laid down on the riverbeds that persisted while the land around them eroded away long after the rivers dried. Similar ghost rivers are seen in desert environments on Earth in Utah, Oman, and Egypt, where erosion rates are slow. The identification of the ghost rivers allows for Arabia Terra to be identified as a fossilized floodplain, somewhat like the lower sections of the river Ganges on Earth, the lowland interface between mountain rivers and the sea. This is an important discovery because it feeds into a long-standing and still unresolved scientific debate about the nature of the Noachian climate. Nobody disputes that rivers once flowed on Mars, or that many impact craters were once home to lakes. The key question is one of longevity. Was Mars warm and wet for long periods of time, or was it for the most part a frozen planet on which water occasionally melted, perhaps triggered by sporadic volcanic activity or shifts in the planet's orbit? The tension arises because climate modelers find it very difficult to simulate an ancient Martian atmosphere thick enough to deliver a stable climate over hundreds of millions of years that would have been lost at a sufficiently fast rate to produce the Mars we see today. In a recent review, for example, Robin Wordsworth concludes, "The weight of geochemical and geomorphological evidence points towards a late Noachian hydrological cycle that was intermittent, not permanently active. And the latest state-of-the-art Martian climate simulations suggest a water-limited early Mars with episodic melting episodes may be a suitable paradigm for much of the later Noachian and early Hesperian climate." Before the recent analysis of the Mars Global Surveyor data, it was thought that there was a relative absence of river channels on Arabia Terra, and this was interpreted as support for a frozen, episodically wet Mars. Ice may have been concentrated in the southern highlands, and so lower elevations like Arabia Terra may have been generally more arid and therefore devoid of river channels. This appears not to be the case. Arabia Terra was once very wet indeed. This debate has no consensus resolution at the time of writing, which reminds us of important points about both our knowledge of Mars and science in general. We are describing and attempting to understand and contextualize events that happened over 3.5 billion years ago, at or around the time that life on Earth began. That is an immense span of time, during which orbital parameters have changed, solar output has varied, and innumerable impact events have cratered the planets. Tracing the evolution of an atmosphere backwards through time from today's measurements, anchored by geological and geochemical evidence from a few landing sites and orbital imagery, is extremely difficult. Suffice to say, there remains an unresolved tension between Mars's small size and large distance from the Sun, and the clear evidence of an ancient water cycle, episodic or persistent. As Wordsworth writes in the introduction to his review, the nature of the early Martian climate is one of the major unanswered questions of planetary science. The complexity and apparent intractability of the mystery is reason enough for many scientists to study Mars. The character of the scientist requires not only comfort with, but attraction to the unknown, an acceptance of and delight in the complexity of nature. There is no simple story of any planet. They are each too big and too old and subject to too many variables. We might reflect on what that means for our own existence, as individuals and as a species. The specific fact of our existence is inextricably linked with the evolution of our planet through an incomprehensible web of cause and effect stretching back via major and minor events, many beyond Earth itself, and filtered by the multidimensional sieve of evolution by natural selection. This connects us with every living thing that went before, back to the origin of life almost 4 billion years ago, and the origin of our planet 500 million years before that, and the origin of the solar system and the laws of nature who knows when, perhaps during the Big Bang, or perhaps infinitely far away in time. There's a lot we can't know. The search for certainty is a fool's errand, and the lesson is to find delight in not knowing, while simultaneously committing to extending the domain of the known. That's the key to science, the key to happiness, and the only reasonable response to the existential challenge of existence, because it is the truth. If you don't like that, comfort yourself with the fact that the domain of the knowable is vast, possibly infinite, and perhaps paradoxically, the knowable things about Mars may exceed those about Earth. Because Mars has been in deep geological freeze for much of its life, it is easier to research the deep past than it is on Earth. And that deep past may include the origin of life. Traces of the geochemical alchemy that led to the emergence of self-replicating, information-carrying carbon molecules on Earth 4 billion years ago weathered away long ago, although clues may be found in the common structures and chemistry of living things today. On Mars, however, geochemistry was frozen and archived in regions such as Arabia Terra. If, therefore, life began or even still exists subsurface on Mars, such a discovery may deliver insight into our own origins that would simply not be possible by studying the weathered, ever-changing ecosystems of Earth. This may be the gift of unknowable Mars. She's less unknowable than Earth. The Eridania region of the Southern Highlands may provide the most compelling evidence yet of a warm, wet, early Mars, with conditions not dissimilar to Earth at the time when life began. The analysis we describe below is a beautiful example of how the suite of science instruments aboard multiple spacecraft in orbit around Mars can be combined with our knowledge of cratering rates on the Moon to characterize an environment and trace its history back through deep time. It is also a beautiful example of the interconnected nature of science and the value of exploration. We've already met the elevation maps from the MOLA aboard the Mars Global Surveyor. This topological data, in concert with visual data from MRO revealing the location of valley networks, suggests that the Eridania Basin was once a giant lake, possibly the largest ever to exist on Mars, 1.5 kilometers deep in places, and containing 3 times more water by volume than the Caspian Sea on Earth. We know the terrain is late Noachian, around 3.7 billion years old, from crater counting. The CRISM spectrometer on board MRO reveals the mineralogical composition of different areas of the Eridania Basin, and this can be used in conjunction with the topological and visual data to build a 3-dimensional picture of the landscape and its chemical composition. In the deepest areas of the Eridania Basin, magnesium and iron-rich clay minerals are common, laid down as sheets of saponite, talc, serpentine, and so-called tot clays. These are characteristic of seafloor environments on Earth. Materials known as iron-rich phyllosilicates are also seen, which are again characteristic of terrestrial seafloor deposits. The mineral jarosite is detected, suggestive of the chemical weathering of sulfite deposits. There are many different carbonate signatures containing iron, manganese, magnesium, and calcium. Higher up the basin walls, chlorides are found, which are indicative of evaporation in shallower water. The most likely explanation for the origin of the deep clay, carbonate, and sulfite deposits, it's argued, is volcanic activity on the floor of a deep lake, because very similar deposits are seen at hydrothermal sites on Earth. The iron minerals detected are similar to those formed in the iron-rich early oceans of Earth, prior to the release of large amounts of oxygen into our atmosphere by photosynthesis. All this beautiful topological, visual, geophysical, and geochemical data can be combined to produce a picture of what was happening in the Eridania Basin around 3.7 billion years ago. The geochemistry of the low-lying regions is indicative of a deep-sea, volcanically active hydrothermal environment, with the salt-rich deposits at higher elevations suggestive of slow evaporation in shallower waters. The basin contained an iron and mineral-rich ocean, energized by active volcanism deep below the waves. A cauldron of complex geochemistry, stirred by the constant flow of energy from the inner planet. This is a striking conclusion because at the same time, a few 100 million kilometers across the solar system on Earth, many biologists believe that life began in similar deep-sea volcanic environments. The theory that life on Earth began in hydrothermal vent systems is mainstream, although not universally accepted by any means. The idea is partly based on the observation that all living organisms on Earth today share a chemistry associated with the establishment of gradients in the concentration of protons across membranes, known as chemiosmosis. Proton gradients are also characteristic of the geochemistry of alkaline hydrothermal vent systems in acid oceans, which were common on the young Earth and perhaps the young Mars. An analysis published in 2017 claims to have detected evidence of biological activity in rocks laid down by hydrothermal activity at least 3.77 billion years ago in the Nouveau-Guitook crustal belt in Quebec, near the Greenland Ishua rocks. The evidence comes from tube-like coils of the iron oxide mineral hematite, similar in size and form to structures laid down by iron-oxidizing bacteria in hydrothermal environments today. It's possible that the rocks at Nouveau-Guitook are much older. A radiometric date using the samarium-neodymium decay process suggests an age of 4.28 billion years, which would make them by far the oldest rocks on Earth, and an astonishingly early date for biological activity. These findings are controversial, in part because of the difficulty of understanding how Earth's active geology has modified the samples over such vast timescales. This is where Mars may have an advantage over Earth in helping us to understand the processes by which the chemistry of a planet became the chemistry of life. The environment at Eridania is far better preserved than that at Nouveau-Guitook. It has been in sterile, almost deep freeze conditions for over 3 billion years, the ultimate laboratory for studying the origin of life, if indeed life began on Mars. The story of the Eridania Basin and the possible scientific promise it holds was pieced together by using the results from different instruments on different spacecraft over many years, spanning several scientific disciplines: geology, chemistry, spectroscopy, laser altitude ranging, and photography. The estimate of the age of the surface required the Apollo lunar rock samples from 50 years ago, and radiometric dating techniques which required an understanding of nuclear physics. The estimate of the age of the surface requires a model of the entire solar system in order to interpret the measured crater density, which illustrates another important idea. The solar system is a system. No planet is an island. No planet can be understood in isolation, just as the structure of any one living thing on Earth cannot be understood in isolation. Organisms are a product of evolution by natural selection, the interaction of the expression of genetic mutations and mixing with other organisms in the ecosystem and the wider environment. The planets formed in a chaotic maelstrom from motions as random as the impact of a cosmic ray on a strand of primordial DNA. And whatever worlds emerged from the chaos have had their histories shaped profoundly by their mutual interactions throughout their evolution. The late heavy bombardment is a beautiful example. If indeed we discover that life began in the Eridania Basin, what a magnificent illustration of the unity of knowledge that would be. Understanding developed over centuries, the life's work of thousands of explorers, field geologists, chemists, biologists, astronauts, engineers, distilled into the discovery of a second Genesis. But more than that, because of the pristine nature of the ancient environments on Mars, such a discovery would deliver an insight into our own origins that may not be available to us here on Earth. Mars is a time capsule, containing the frozen chemistry of an ancient world similar to the Earth when life began. But while Earth's deep past has been largely erased by 4 billion years of geology and the action of a complex global living ecosystem, which has transformed the planet and its atmosphere beyond all recognition, Mars is a fossil from the deep past. This raises the wonderful possibility that another world, albeit an integral part of our system, may be the key to decoding the mystery of the origin of life here. The reason we exist. It's almost as if we have to leave the cradle in order to truly understand it. Around 3.5 billion years ago, change was underway on Mars. The warmer, wetter episodes that characterized the planet for millions of years during the Noachian became less frequent, and the climate drifted, imperceptibly at first, towards the colder, arid state we recognize today. The water that flowed freely over the surface during the Noachian became locked away in giant reservoirs of ice. Lakes turned solid, and rivers ran dry. The planet wasn't dying, far from it. The fireworks of the late heavy bombardment had faded, but rumbles from the deep maintained the violence. The shield volcanoes of Tharsis, including the mighty Olympus Mons, continued to build even as global temperatures plummeted, and subsurface lava flows occasionally melted the reservoirs of ice, leading to catastrophic floods that challenged the imagination in their scale and violence. The age of Noah became the Hesperian, the age of floods, or rather less portentously and more accurately, the age of occasional floods. The Hesperian period is named after the Hesperia Planum, a giant lava field to the northeast of the Hellas Basin in the southern highlands. The plain was resurfaced partly by the volcano at its center, Tyrrhenus Mons, and spans almost 2 million square kilometers. First photographed by Mariner 9 in 1972, it's a relatively flat landscape with few visible rock formations. The most prominent surface features are the craters that allow us to date it. Tyrrhenus Mons is a very different volcano to Olympus Mons and the giants of Tharsis. It's much more ancient, fully formed not long after the Hellas impact 4 billion years ago, and it erupted through water or frozen ground, a process that produces large amounts of ash rather than lava, what geologists call a pyroclastic eruption. As a result of its age and composition, Tyrrhenus was more prone to erosion than the giants of Tharsis, and today stands only 1.8 kilometers above Hesperia Planum. The Hesperian period was coincident with increased volcanic activity, particularly at Tharsis. But there's not necessarily a causal link between volcanic activity and the transition from the Noachian to the Hesperian. What is clear is that volcanism became the dominant geological force on Mars as the long-lived water cycles waned and cratering rates declined after the late heavy bombardment around 3.5 billion years ago. This is seen in both surface features and mineralogy. Hesperian surfaces are richer in sulfates rather than the clays and carbonates of the Noachian. Sulfates form in the more acidic atmospheric conditions created by the release of sulfur dioxide from volcanoes. While volcanic activity was the dominant force sculpting the smoother Hesperian landscapes, there are spectacular and notable exceptions where water reasserted its dominance, if only for a moment. Ekus Chasma is an unremarkable valley today. Images taken by MRO reveal a deep, steep-sided depression lying to the north of the Mariner Valley. At 100 kilometers long, 10 kilometers wide, and between 1 and 4 kilometers deep, it would be impressive on Earth, but is dwarfed by the magnificent neighboring valley system. 3.5 billion years ago, on frozen Hesperian Mars, however, things were different. High above, on the Tharsis Rise, lava surged upwards through the crust and met great reservoirs of ancient ice, releasing vast amounts of water that raged down from the southern highlands. The meltwater was funneled towards Ekus Chasma, where it created one of the briefest and yet most spectacular wonders of the solar system. The waters from the highlands came tumbling over the cliffs, roaring 4 kilometers down into the valley below, over the largest known waterfall in the history of the solar system. Around 350,000 cubic kilometers of water cascaded through the valley, the equivalent of a cube 70 by 70 by 70 kilometers, in less than 2 weeks. This being Hesperian Mars, the atmosphere was not substantial enough for the liquid to persist on the surface, and the water disappeared as quickly as it came, leaving scant evidence of the great falls, etched into the canyon walls. Echo's chasma was unique in scale, but the cycle of volcanic eruption followed by fleeting catastrophic floods was repeated in many locations across the planet throughout the Hesperian. However, in the thinning atmosphere, the presence of liquid water was probably always fleeting, increasingly so as time passed. Hesperian became Amazonian around 3 billion years ago, plus or minus 500 million years or so. When a Mars expert is asked the question, when did the Amazonian begin, they will usually say, depends who you ask. But certainly by 2 billion years ago, long before there was complex multicellular life on Earth, Mars was pretty much indistinguishable from the planet we see today. The red planet didn't die entirely. Volcanic eruptions persisted and have occurred in the very recent past at Tharsis. There may yet be eruptions in the future. But we do know that Mars changed from a world that supported liquid water on the surface under a thick atmosphere, via a period dominated by intense volcanic activity and episodic floods, into a hyper-arid frozen planet with a tenuous atmosphere, more befitting its small size and place in the solar system. This drama played out very roughly during the first 1.5 billion years of its life. The challenge is to understand why. Losing atmosphere. The climate of a rocky planet is a complex dynamic system shaped by myriad interactions, feedbacks, and instabilities, and inevitably changes over geological timescales. The thin envelope of atmospheric gases can be affected dramatically by volcanic and tectonic activity and impacts from space, and on longer timescales by shifts in orbit and tilt, and changes in solar output. Earth seems to be a remarkable exception. The most dramatic atmospheric change over the last 3 billion years has been the gentle introduction of oxygen by photosynthesis. Mars today has a thin atmosphere composed primarily of carbon dioxide. We know this atmosphere must have been significantly thicker in the past, quite possibly at an even higher pressure than that of modern-day Earth, because there was once liquid water on the surface. Mars must therefore have lost most of its original atmosphere, and it's important to understand where it went and why. The ancient atmospheric carbon dioxide molecules could have frozen out onto the surface in the polar ice caps, become locked away in the subsurface as carbonate minerals, or they could have been lost to space, or some combination of all three. To measure the composition of the Martian atmosphere today and understand how it evolved over time, a dedicated mission arrived in orbit in September 2014. MAVEN, the Mars Atmosphere and Volatile Evolution mission, has no high-definition cameras and provides no dramatic photographs of the surface, because the questions MAVEN was designed to answer are about the invisible envelope of gases surrounding the planet. If curiosity is the extension of our hands and MRO our eyes, MAVEN is our nose, sniffing the air for clues to the past. The spacecraft operates in a highly elliptical orbit, bringing it as close as 150 kilometers above the surface and out beyond 6,000 kilometers. This eccentric path means that on every orbit, MAVEN experiences a wide profile of the Martian upper atmosphere, allowing it to build a three-dimensional picture of the gases that still remain and how their distribution changes with altitude and time. MAVEN's measurements show that Mars is losing atmospheric gases today at a rate of about 2 kilograms a second. The question is, how is the atmosphere being lost, and where is it going? The MAVEN team carried out an ingenious analysis based on observations of the concentrations of two different isotopes of the noble gas argon, argon-36 and argon-38. Argon-38 is chemically identical to argon-36, but it's heavier because it has two additional neutrons inside its nucleus. The ratio of argon-38 to argon-36 is sensitive to the rate at which the atmosphere is being lost to space through a process known as sputtering. High-speed, electrically charged particles from the solar wind hit atoms in the upper atmosphere and literally knock them out into space. Because argon-36 is lighter than argon-38, The relative abundance of argon-36 in the upper atmosphere is enhanced. In technical terminology, argon-36 has a larger scale height than argon-38. This means that argon-36 is preferentially lost to space through sputtering, and the ratio of argon-38 to argon-36 increases. Since there's no other way that argon can be removed from the atmosphere, it doesn't react with anything, and it doesn't freeze at anywhere near the temperatures seen on Mars, the argon measurements provide a very clean indication of the way the Martian atmosphere is affected by the solar wind. By using measurements from MAVEN at different altitudes during its elliptical orbit, and surface measurements of the argon isotope ratio from Curiosity, this beautifully elegant experiment enabled the team to determine that 66% of the argon in the Martian atmosphere has been lost over the planet's 4.5 billion year lifetime. Once this rate of argon loss has been determined, the rate of other atmospheric components can be calculated. The published results concluded: the evidence from MAVEN observations suggests that a large fraction of the Martian volatile inventory has been removed to space, and that loss to space has been an important process in the evolution of the Martian atmosphere through time. In particular, a large fraction of the dominant component of the Martian atmosphere, the powerful greenhouse gas carbon dioxide, has been lost to space through the interaction with the solar wind, with a smaller fraction being locked away in subsurface carbonate deposits, and an even smaller fraction stored as frozen carbon dioxide in the polar ice caps. These changes, the authors conclude, appear to be large enough to account for the change in the Martian climate inferred from the planet's geomorphology. Without declining levels of greenhouse gases in the atmosphere to keep in warmth and protect its lakes and oceans, Mars was destined to become a frozen desert world. But why has Earth not suffered the same fate? We are, after all, closer to the Sun, and bathed in a more violent solar wind. Why has our atmosphere survived the solar onslaught for several billion years, after the Martian atmosphere was stripped away?
Nicolaus Copernicus was born in the Polish city of Torun in 1473 and benefited from a superb education after being enrolled at the University of Krakow at 18 by his influential uncle, the Bishop of Warmia. In 1496, intending to follow in the footsteps of his uncle, Copernicus moved to Bologna to study canon law, where he lodged with an astronomy professor, Domenico Maria de Novara, who had a reputation for questioning the classical works of the ancient Greeks, and in particular their widely accepted cosmology. The classical view of the universe was based on Aristotle's not unreasonable assertion that the Earth is at the centre of all things and that everything moves around it. This feels right, because we don't perceive ourselves to be in motion, and the sun, moon, planets and stars appear to sweep across the sky around us. However, a little careful observation reveals that the situation is in fact more complicated than this. In particular, the planets perform little loops in the sky at certain times of year, reversing their track across the background stars before continuing along their paths through the constellations of the zodiac. This observational fact, which is known as retrograde motion, occurs because we are viewing the planets from a moving vantage point, the Earth, in orbit around the Sun. This is by far the simplest explanation for the evidence, although it is possible to construct a system capable of predicting the positions of the planets months or years ahead and maintain Earth's unique stationary position at the centre of all things. Such an Earth-centered model was developed by Ptolemy in the 2nd century and published in his most famous work, Almagest. The details are extremely complicated and aren't worth describing in detail here because the central idea is totally wrong and we won't learn anything. The sheer contrived complexity of an Earth-centered description of planetary motions can be seen in Ptolemy's model, which shows the apparent motions of the planets against the stars as viewed from Earth. This tangled Ptolemaic system of Earth-centered circular motions, replete with the arcane terminology of epicycles, deferents, and equant, was used successfully by astrologers for thousands of years to predict where the planets would be against the constellations of the zodiac, presumably allowing them to write their horoscopes and mislead the gullible citizens of the ancient world. And if all you care about are the predictions themselves, and your philosophical prejudice and common sense feeling of stillness require the Earth to be at the centre, then everything is fine. And so it remained until Copernicus became sufficiently offended by the sheer ugliness of the Ptolemaic model to do something about it. Copernicus's precise objections to Ptolemy are not known, but sometime around 1510 he wrote an unpublished manuscript called the Commentariolus, in which he expressed his dissatisfaction with the model. I often considered whether there could perhaps be found a more reasonable arrangement of circles, from which every apparent irregularity would be derived, while everything in itself would move uniformly, as is required by the rule of perfect motion. The Commentariolus contained a list of radical and mostly correct assertions. Copernicus wrote that the moon revolves around the Earth, the planets rotate around the sun, and the distance from the Earth to the sun is an insignificant fraction of the distance to the stars. He was the first to suggest that the Earth rotates on its axis, and that this rotation is responsible for the daily motion of the sun and stars across the sky. He also understood that the retrograde motion of the planets is due to the motion of the Earth and not the planets themselves. Copernicus always intended Commentariolus to be the introduction to a much larger work, and included little, if any, detail about how he had come upon such a radical departure from classical ideas. The full justification for and description of his new cosmology took him a further 20 years, but by 1539 he had finished most of his 6-volume De Revolutionibus, although the completed books were not published until 1543. They contained the mathematical elaborations of his heliocentric model, an analysis of the precession of the equinoxes, the orbit of the moon, and a catalogue of the stars, and are rightly regarded as foundational works in the development of modern science. They were widely read in universities across Europe and admired for the accuracy of the astronomical predictions contained within. It's interesting to note, however, that the intellectual turmoil caused by our relegation from the centre of all things still coloured the view of many of the great scientific names of the age. Tycho Brahe, the greatest astronomical observer before the invention of the telescope, referred to Copernicus as a second Ptolemy, which was meant as a compliment, but didn't accept the sun-centred solar system model in its entirety, partly because he perceived it to be in contradiction with the Bible, but partly because it does seem obvious that the Earth is at rest. This is not a trivial objection to a Copernican solar system, and a truly modern understanding of precisely what at rest and moving mean requires Einstein's theories of relativity, which we'll get to later. Even Copernicus himself was clear that the sun still rested at the centre of the universe. But as the 17th century wore on, precision observations greatly improved due to the invention of the telescope and an increasingly mature application of mathematics to describe the data, and led a host of astronomers and mathematicians, including Johannes Kepler, Galileo, and ultimately Isaac Newton, towards an understanding of the workings of the solar system. This theory is good enough even today to send space probes to the outer planets with absolute precision. At first sight, it's difficult to understand why Ptolemy's contrived mess lasted so long, but there is a modern bias to this statement that is revealing. Today, a scientifically literate person assumes that there is a real, predictable universe beyond Earth that operates according to laws of nature, the same laws that objects obey here on Earth. This idea, which is correct, only emerged fully formed with the work of Isaac Newton in the 1680s, over a century after Copernicus. Ancient astronomers were interested primarily in predictions, and although the nature of physical reality was debated, the central scientific idea of universal laws of physics had simply not been discovered. Ptolemy created a model that makes predictions that agree with observation to a reasonable level of accuracy, and that was good enough for most people. There had been notable dissenting voices, of course. The history of ideas is never linear. Epicurus, writing around 300 BCE, proposed an eternal cosmos populated by an infinity of worlds, and around the same time Aristarchus proposed a sun-centred universe about which the Earth and planets orbit. There was also a strong tradition of classic orthodoxy in the Islamic world in the 10th and 11th centuries. The astronomer and mathematician Ibn al-Haytham pointed out that whilst Ptolemy's model had predictive power, the motions of the planets represent an arrangement that is impossible to exist. The end of the revolution started by Copernicus around 1510, and the beginning of modern mathematical physics can be dated to the 5th of July 1687, when Isaac Newton published the Principia. He demonstrated that the Earth-centered Ptolemaic jumble can be replaced by a Sun-centered solar system and a law of universal gravitation, which applies to all objects in the universe and can be expressed in a single mathematical equation: F equals G times m1 m2 over r squared. The equation says that the gravitational force between two objects, a planet and a star, say, of masses m1 and m2, can be calculated by multiplying the masses together, dividing by the square of the distance r between them, and multiplying by g, which encodes the strength of the gravitational force itself. G, which is known as Newton's constant, is, as far as we know, a fundamental property of our universe. It is a single number which is the same everywhere and has remained so for all time. Henry Cavendish first measured G in a famous experiment in 1798, in which he managed, indirectly, to measure the gravitational force between lead balls of known mass using a torsion balance. This is yet another example of the central idea of modern physics. Lead balls obey the same laws of nature as stars and planets. For the record, the current best measurement of G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, which tells you that the gravitational force between two balls of mass 1 kilogram each 1 meter apart is just less than 10,000 millionths of a Newton. Gravity is a very weak force indeed, and this is why its strength was not measured until 71 years after Newton's death. This is a quite brilliant simplification, and perhaps more importantly, the pivotal discovery of the deep relationship between mathematics and nature which underpins the success of science, described so eloquently by the philosopher and mathematician Bertrand Russell. Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. Nowhere is this sentiment made more clearly manifest than in Newton's law of gravitation. Given the position and velocity of the planets at a single moment, the geometry of the solar system at any time millions of years into the future can be calculated. Compare that economy. You could write all the necessary information on the back of an envelope, with Ptolemy's whirling offset epicycles. Physicists greatly prize such economy. If a large array of complex phenomena can be described by a simple law or equation, this usually implies that we are on the right track. The quest for elegance and economy in the description of nature guides theoretical physicists to this day, and will form a central part of our story as we trace the development of modern cosmology. Seen in this light, Copernicus assumes even greater historical importance. Not only did he catalyze the destruction of the Earth-centered cosmos, but he inspired Brahe, Kepler, Galileo, Newton, and many others towards the development of modern mathematical physics, which is not only remarkably successful in its description of the universe, but was also necessary for the emergence of our modern technological civilization. Take note, politicians, economists, and science policy advisors of the 21st century. A prerequisite for the creation of the intellectual edifice upon which your spreadsheets, air-conditioned offices, and mobile phones rest was the curiosity-driven quest to understand the motions of the planets and the Earth's place amongst the stars. Matching the observations of the wandering stars, the planets, of the night sky with the idea that the Earth was at the center of the solar system required extremely complex models. In the case of Venus, combining the Earth at the center with the observations meant that Venus had a circular orbit around a point midway between the Earth and the Sun, so-called epicycles, with all the other planets having similar complicated orbits around various points scattered around the solar system. Placing the Sun at the center of the solar system, with the planets arranged in their familiar order, with the Moon orbiting the Earth, gave a much simpler system.